Hello and welcome to this A-level chemistry explanation video about the transition metals. This is one of the most important topics in all of A-level chemistry, and I will go into detail about all the different parts that it includes. The periodic table is split up into different regions called blocks, and these blocks are called the S, P, D and F blocks. They take their name from the outermost occupied subshell, or sometimes called sublevel. So for all of the elements in the S block, their outermost electrons are in an s orbital. If an element's outer electrons are in a p subshell, they are in the p block. This region in the middle of the periodic table here is the D block, and it's in the D block that we find the transition metals. The top row of the D block of the periodic table contains 10 elements, all of which are metals whose outer electrons are in a D subshell. The transition metals are the elements titanium through to copper, and they have some distinctive properties that make them quite different to the metals in groups 1 and 2. When working out the electron configuration, we need to remember that we fill the lowest energy sublevel first before moving to putting electrons into the next sublevel. And sublevels are split into orbitals, which are filled singly before electrons start sharing orbitals. So as an example, let's look at argon. It has got an atomic number of 18, which means it's got 18 protons and 18 electrons. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. For D block elements, it's important to remember that we fill the 4s subshell before moving on to fill the 3D. So for titanium, as an example, which has got an atomic number of 21, so that means it's got 3 more electrons than argon has, its outer electron configuration is 3d1, 4s2. And that means that the 4s subshell is filled, and we're in the process of filling the 3d subshell. Remember, the D sublevel has 5 orbitals, each holding 2 electrons, so potentially up to a total of 10 electrons. And we can see this pattern if we look at the top 10 elements in the D block from scandium through to zinc. You can see that I'm showing the electron configuration of argon as a shortcut, so I don't have to keep writing it all those 10 times. And I'm just focusing on the 3D and the 4s subshells so we can see how those are filled. And you can see that the pattern of filling the 4s before the 3d is kept to mostly across the top row of the D block, with the exceptions of chromium, which has a precisely half-filled D subshell and S subshell, and copper, which has an entirely filled D subshell and a partly filled S subshell. And those are exceptions that you need to know where those elements are slightly more stable as a result of that particular electron configuration rather than the one that you might expect. The definition for transition metals is to do with their ions that they form. Metal atoms generally form positive ions by losing electrons, and another rule for the D block elements is that they lose the 4s electrons before the 3d. Transition metal elements, for instance those between titanium and copper, get their characteristics because they form at least one stable ion with an incomplete D subshell. So for instance, titanium can form the stable ion titanium 3+, and so it will lose 3 electrons from its outermost shells, and that will give it the electron configuration that I'm showing here. And you can see that it has lost the s electrons, and it has a partially filled D subshell in the 3d1 configuration. Here are examples of stable ions for the other 9 elements in the top row of the D block. You can see that for the ions titanium through to copper, the examples that I'm showing are stable ions with an incomplete 3D subshell. Scandium and zinc are exceptions. Scandium typically only forms a 3+ ion, which means its D subshell is in fact empty. Zinc typically only forms a 2+ ion, and it loses its 4s electrons to do so, and so the 3d subshell is in fact entirely full. Therefore, scandium and zinc are not considered to be transition metals because they do not form stable ions with an incomplete d subshell. Transition metal characteristics of elements titanium to copper arise from an incomplete d sublevel in at least one stable ion. These properties include complex formation. The formula of a complex looks something like this one containing copper ions. More about this in a moment. Transition metals have variable oxidation states. For example, iron can readily form iron 3+ and iron 2+ ions. Transition metals can form coloured ions. For example, iron 3+ forms a yellow solution and iron 2+ forms a green solution. Transition metals also display catalytic activity. For example, nickel is the catalyst when hydrogen is used in the reduction of aldehydes and ketones. Since scandium and zinc do not form stable ions with an incomplete d sublevel, they are not transition metals, and so they do not have these properties. For instance, they generally form white solids and are colourless in solution. A complex is a central metal atom or ion surrounded by ligands, and a ligand is a molecule or ion that forms a coordinate bond, also known as a dative covalent bond. And it does this by donating a pair of electrons into an empty or partially filled d orbital of the metal. And so the formula of the complex might look something like this, with a copper metal, that's the electron pair acceptor, also sometimes called a Lewis acid, and we can see that the ligands on this occasion are water molecules, the electron pair donors, and so to be a ligand something must have an electron pair to donate, a lone pair, and this is sometimes referred to as a Lewis base. And you can see in this formula there are actually 6 water ligands. And the coordinate bond itself comes from a lone pair on the oxygen atom in the water ligand, and that electron pair is donated to the metal copper. Unless we're specifically told to do so in an exam question, you won't be expected to show the lone pair and the arrow in an exam question. They're typically more interested in showing the shape of the complex. And so the complex that I've shown here would have this octahedral shape, and you can see that the way I'm showing the bonds, we're giving some acknowledgement to the 3-dimensional space filling of these ligands. If the complex carries an overall charge, like this one I'm showing here, it is referred to as a complex ion. And most commonly in exam questions, you will encounter complexes as complex ions. And when you write the formula or show the shape of a complex ion, it's really important to show the formula or the shape inside square brackets like I'm doing here, and have the overall charge on display in the top right-hand corner. The coordination number of the complex is the number of coordinate bonds to the central metal atom or ion. Most common coordination numbers are 6 and 4. And the most common complex you'll encounter here is the hexa-aqua complex, like the one I've shown here, which is called hexa-aqua copper 2. And in general, we'll see the formula of the complex with, I'm showing here M for any generic metal, 6 water ligands, and typically the complex will have a 2+ charge or a 3+ charge. And this is the complex that forms when any metal compound dissolves in water. Ligands are classified by the number of coordinate bonds they can form with a metal ion. Monodentate ligands can form 1 coordinate bond to a metal ion. And the term dentate comes from the Latin word for teeth, and it describes how ligands bite onto a metal ion, forming, in this case, a single coordinate bond. Examples of monodentate ligands include water, ammonia, and the chloride ion. And you can see from the diagrams that I'm showing here the shapes of these ligands and the lone pairs that are available to form coordinate bonds. The water ligand and the chloride ion have multiple lone pairs, but they can still only form one coordinate bond each. And that's because their geometry prevents multiple lone pairs from bonding to the same metal. Ammonia and water are a similar size and uncharged. The chloride ligand, as well as having a negative charge, is larger than the ammonia and the water, and this affects the shape of complexes with chloride ligands. Transition metal ions commonly form octahedral complexes with small ligands, for instance with water ligands and with ammonia ligands. I'm showing the formula of a complex ion here. We've got copper and we've got 6 water ligands and a 2+ charge overall. This will form an octahedral shape like I'm showing here. You need to be able to draw complex ions like this, giving a clear indication of the spatial arrangement of those bonds and those ligands. We need to show the square brackets around the outside and the overall charge that's being carried by this complex. Another example is this cobalt complex with 6 ammonia ligands. Again, we've got a 2+ charge overall, so again we need the square brackets with the 2+ on the outside and a clear indication of the octahedral shape, and all the bond angles need to be 90 degrees. Transition metal ions commonly form tetrahedral complexes with larger ligands, and that's because there's not enough room for 6 ligands to fit. They literally take up too much of the available space. An example of this is the chloride ligand. And so in the complex with copper ions, we can only fit 4 chloride ions around the central copper ion. And so we get a tetrahedral shape, and the bond angles will be 109.5 degrees. And so this copper complex with CuCl4 as its formula needs the square brackets around the outside and the 2- charge overall. Bidentate ligands are able to form 2 coordinate bonds to a metal ion, and there are 2 bidentate ligands that you need to know. The first is the ethane dioate ion, which has got the formula C2O4, and it's a 2- ion. And you might find this ion in something like ethane dioic acid or sodium ethane dioate. When we see the displayed formula for this ion, you can see the 2 oxygen atoms that have the lone pairs through which the 2 coordinate bonds can form. And when we make a complex ion using these ligands, we end up with 3 bidentate ligands typically bonding to the metal, forming an octahedral complex. And so the formula for the complex ion would be Fe and then C2O4 inside rounded brackets with a little 3 afterwards to show that there are 3 of this bidentate ligand. And then we need the square brackets around the outside, and this ion has a 3- charge overall, meaning that this was an iron 3+ ion before those ligands bound together to give it an overall charge of 3-. And we can see from this diagram here the octahedral arrangement, those 6 coordinate bonds around the iron ion, and so the coordination number is 6 as a result of that. And here are the 3 ethane dioate ions in those 3 positions around the octahedral complex. The other bidentate ligand that you need to know is ethane 1,2-diamine. And this is its structural formula here. And it's only when we see the displayed formula or the skeletal formula for this ligand that we see the 2 points that coordinate bonds can form from on these 2 nitrogen atoms this time. And again, 3 of these ligands would bond to an iron ion, for instance, and we would get the complex like so, Fe, and then the formula for the ethane 1,2-diamine ligand. We've got 3 of them, and overall this time I'm giving it a 2+ charge because I'm saying that the iron is a +2 ion. And since this is really quite a long formula, the ligand is sometimes abbreviated to En, instead of writing the formula for ethane 1,2-diamine as I did at first. And if we were abbreviating it like this, the formula would be significantly easier to write. We'd retain the square brackets and the 2+ charge overall, and of course the symbol for iron is unchanged, but that structural formula for the ligand is removed and we replace it with the En, and we still need those 3 afterwards to show that there are 3 of this bidentate ligand. Multidentate ligands form many coordinate bonds to a metal ion. One example that you need to know is the EDTA 4- ion. EDTA is an abbreviation and it stands for ethylene diamine tetraacetic acid. But as a ligand, it will be the 4- ion, and here is its structure as I'm showing like this. You won't be required to remember the formula or to draw it, but you need to know that it's a multidentate ligand, and you need to be able to identify where it can form coordinate bonds. And it can in fact form 6 coordinate bonds. And you could be asked to circle the atoms with lone pairs that it could use to form those coordinate bonds. And because it can form 6 coordinate bonds, there must of course be 6 atoms to circle. 2 of them are the nitrogen atoms in the middle, and the other 4 are these 4 atoms that I'm showing here, the oxygen that are carrying the negative charge, and I'm showing them with the lone pair here. You also need to be able to write formulae and equations working with complexes containing the EDTA ligand. For instance, we've got 2 formulae for complex ions here, one with an iron metal and one with copper. For the iron, the overall charge is -1, and so that means iron plus EDTA 4- will have a -1 charge overall. Therefore, iron -4 is equal to -1, and so the iron metal must have a +3 charge on this occasion. And since the overall charge for the copper complex is 2-, copper must be +2 as a result. You need to be able to draw the shape of complex ions. Typically, there will be an octahedral or tetrahedral shape, and it's most likely that it will include the ligands mentioned in this video, but it might be for something unfamiliar. And complex ions can contain more than one different type of ligand. An example of this is the compound that I'm showing here, and it's an ionic compound with this complex and a chloride ion. And since the chloride ion is a negative ion, the complex must be positive overall. And so we've got the chromium metal and 6 monodentate ligands, 4 ammonia and 2 chloride ions. That means that this will be a complex with an octahedral shape. And so we've got our central transition metal, we've got our 6 coordinate bonds around that metal, and I'm showing the spatial arrangement as well, and then we need to add our 6 ligands, add the brackets, and then put in the overall positive charge. You could also be asked to work out the oxidation state of a metal in a complex ion. For instance, for this one here, the overall charge of the complex is +1. We've got a chromium metal, we've got 4 neutral ammonia ligands and 2 negative chloride ligands. And so that means that chromium plus 4 lots of 0 plus 2 lots of -1 equals +1 overall. So chromium plus 0 minus 2 is equal to +1, and that means that the oxidation state of the chromium must be +3. Sometimes complex ions can have a linear shape. And an example of this that you need to know is Tollens reagent. And this is what you get when silver ions with a charge of 1+ combine with 2 neutral ammonia ligands. And they take up the linear shape because the electron clouds in those 2 coordinate bonds move until they're as far apart as possible in 3-dimensional space, which is 180 degrees. When this complex is used as Tollens reagent, what we get is reduction of the complex to metallic silver in the presence of aldehydes. To make this happen, you would take a water bath, because this only works when the chemicals are warmed. You'd get a boiling tube of one compound, perhaps the aldehyde, and then another with the ketone. You'd add Tollens reagent to both of them, and the aldehyde would be the one that gives you the silver mirror that forms. The ketone would display no visible change. The equation for this reaction has got the aldehyde reacting with 2 of the complex of Tollens reagent in alkaline conditions, so we need 3 OH- ions, and that gives us the oxidized form of the aldehyde, which would be the carboxylate ion. We'd get the silver that has been reduced from 1+ to silver 0. We've got our 4 ammonia, and we've got 2 water as our final product. We also need to know that Tollens is produced when the silver halide precipitate dissolves in the presence of ammonia solution. For example, silver chloride will dissolve in dilute aqueous ammonia, and silver bromide, the cream precipitate, will dissolve in concentrated ammonia, and the complex ion that forms is Tollens reagent along with the bromide ion. Complexes can display stereoisomerism. This is where two things have the same structural formula but a different spatial arrangement. Octahedral complexes can display cis-trans isomerism with monodentate ligands. Remember, examples of that are water, ammonia, and the chloride ion. Cis-trans isomerism is a form of geometric isomerism, and in this the ligands differ in their positions in space relative to each other. Cis-trans isomerism follows the same principles as EZ isomerism, but cis-trans isomerism is used when we have two identical ligands, and these ligands might be next to each other or they might be opposite each other. So in this first complex, we're showing the cis isomer, which is equivalent to the Z isomer. And I'm showing here this copper complex with 4 water ligands and 2 hydroxide ligands. And this is the cis isomer because the 2 hydroxide ligands are next to each other. Whereas, if the 2 hydroxide ligands are opposite each other, we will have the trans isomer of this complex, which is equivalent to the E isomer in EZ isomerism. It isn't only octahedral complexes that display geometrical isomerism. Platinum-2 complexes adopt a square planar geometry rather than tetrahedral, since this is more stable due to the electron configuration of the platinum ion. And square planar complexes can also display cis-trans isomerism. The most common example of this is Cisplatin, which is an anti-cancer drug. It has the formula PT-NH3-2Cl2, which means that there are 2 neutral ammonia ligands and 2 negative chloride ligands. And the platinum ion has a +2 charge, and so therefore overall this complex is neutral. In cisplatin, the 2 chloride ligands are together, next to each other. And in the stereoisomer transplatin, the 2 chloride ligands are opposite each other. And so both of these stereoisomers have the same formula, but they have a different spatial arrangement. And it is only cisplatin that is able to act as the anti-cancer drug. The transplatin has the wrong arrangement of its ligands. Octahedral complexes can display optical isomerism when there are at least 2 bidentate ligands. Remember, optical isomerism is where you get 2 non-superimposable mirror images, and the bidentate ligands that you need to know are ethane 1,2-diamine and the ethane dioate ion. So as an example, if we had a cobalt 2+ complex with 3 bidentate ethane 1,2-diamine ligands, one of the optical isomers could look like this. You can see here these are the 3 bidentate ligands. The spatial arrangement is all important here. Those wedges are coming out towards us and those dashed lines are moving away from us. If we put a mirror here and we draw the mirror image of this complex, right now these 2 complexes look identical. But if one of the isomers, for instance the one on the right, is rotated 180 degrees, 2 of the bidentate ligands now have different spatial arrangements to the other optical isomer. If we consider this bidentate ligand at the top here, this bond is pointing upwards and the other bond for the bidentate ligand is pointing away from us. If this isomer rotates 180 degrees, the coordinate bonds become upwards and towards us. And then the one at the bottom currently is shown as one of the coordinate bonds going downwards and the other one coming out towards us. But if this rotates 180 degrees, the bonds will become down and away from us. And so whilst they look the same, their spatial arrangements are different. You need to be able to draw cis, trans, and optical isomers when given the formula for a complex. And when drawing optical isomers, you would only need to draw the two diagrams that I'm showing here either side of the mirror, not the rotated complex. And you also need to be able to describe the type of stereoisomerism shown by different molecules or complexes. In a complex, one ligand can be replaced by another, and this is called a ligand substitution reaction. Exchange of the ligands ammonia and water occurs without change of coordination number. For instance, if we have the hexa-aqua-cobalt-2 complex that I'm showing here, and we add ammonia to it, perhaps by adding concentrated ammonia solution, what happens is all 6 of those water ligands get replaced by 6 ammonia ligands. And so we end up with a new complex, which is still octahedral, still got 6 ligands attached to the central cobalt, but now we've got 6 water molecules that have been removed from that complex and replaced by ammonia. Sometimes the substitution of ligands may be incomplete, and the example of this that you need to know is when hexa-aqua-copper is reacted with an excess of ammonia. On this occasion, only 4 water ligands are replaced with 4 ammonia ligands. And so the equation looks like this, with the complex being reacted with 4 ammonia molecules, and we end up producing this new complex and 4 substituted water ligands. The exchange of water ligands by a chloride ion can involve a change of coordination number. For instance, if we add concentrated hydrochloric acid to metal aqua ions, we get a change of coordination number from 6 to 4. You can see this in the equations that I'm showing here. If we start with a blue solution of hexa-aqua-copper 2+, and we add concentrated hydrochloric acid, what will happen is all 6 of those water ligands will be removed from the complex, and they will be replaced with 4 chloride ions as ligands instead. And so the equation shows the 4 chloride ions being added and the 6 water molecules being removed. And of course the complex changes as a result. And as a result of the coordination number changing, the shape of the complex changes as well, going from octahedral to tetrahedral. And remember, this happens because the chloride ion is a larger ligand, and so only 4 chloride ions can fit around the copper. This works in the exact same way if you have a different complex, for instance a pink solution of hexa-aqua-cobalt-2 reacting with concentrated hydrochloric acid will produce a blue solution of this tetrahedral cobalt with 4 chloride ions as ligands, and 6 water molecules will be removed. And that's the same thing for when this iron 3 complex is reacted. We add 4 chloride ions and we produce the tetrahedral iron chloride complex, which is still a yellow colour in fact, and then we remove the 6 water ligands. Bidentate ligands and multidentate ligands replace monodentate ligands from complexes much more readily than one monodentate ligand replacing another. And this is known as the chelate effect. And the word chelate comes from the Greek word for chlor, which is the perfect analogy for how these ligands work. They grip the metal ion at multiple points, forming a much more stable complex. And this is what we're referring to when we mention the chelate effect. The explanation for this effect comes from thermodynamics and free energy. If we remember the free energy equation, we can see that we've got delta G equals delta H minus T delta S. And delta G is therefore affected by 2 things, the enthalpy change and the entropy change. And in order for a reaction to be feasible, delta G needs to be less than or equal to 0. So in terms of enthalpy change, if there is no change in coordination number, that means we'll have the same number of coordinate bonds being broken as are being made. And in general, coordinate bonds are similar in terms of their enthalpy, so there will be an enthalpy change that is very close to 0, and so we can say that delta H is negligible. When it comes to the entropy change, if a substitution involves an increase in moles of particles, this will be a positive entropy change. In other words, there will be an increase in disorder. And since delta H is effectively zero and delta S is positive, when we work out delta G, we're subtracting a positive number away from zero, which means that the free energy change is going to be negative, and this ligand substitution is going to be feasible. As an example, if we see this hexa-aqua-copper complex reacting with 3 bidentate ethane dioate ligands, we've got 4 particles in solution in our reactants. If all of those water ligands get substituted out, and we end up with 7 particles in solution as our products. And so this is an increase in disorder, a positive entropy change. We see this even more if we've got our hexa-aqua-copper complex and the EDTA ligand, this multidentate ligand. We have only 2 particles in solution in our reactants. But then when we make the new complex and we substitute out all 6 of the water ligands, we end up with 7 particles in solution. And so this is a very large increase in disorder. And so this reaction, this ligand substitution, will happen very readily. And it's worth noting that if the forward reaction has a negative delta G, the reverse reaction will have a positive delta G. And this means that the reverse reaction is less feasible. And that's what we mean when we say that the product is very stable. It will not readily turn back into the reactant. Heme is an iron 2 complex with a multidentate ligand, and it's a crucial example of ligand substitution that takes place in our bodies. The heme group is comprised of an iron 2 plus ion and a porphyrin ring, which works around the square plane of this iron 2 plus ion and forms 4 coordinate bonds through nitrogen atoms to the central ion. And then actually there are 6 coordinate bonds overall. This one going downwards is to a protein called globin, which is how hemoglobin gets its name. And the coordinate bond going upwards is actually to an oxygen molecule. And this makes up hemoglobin, which is the structure where we've got oxygen at the top. And this oxygen binds reversibly to the iron 2+. That's really important because what that does is it allows the oxygen to be transported in the blood, and then the coordinate bond breaks, releasing the oxygen so it can be used in aerobic respiration. And a molecule of water takes its place. And so this is an example of reversible ligand substitution, as one ligand, the oxygen, is swapped for another, the water. And once the oxygen has been substituted out, we have a new molecule called deoxyhemoglobin. And that's when we've got the water in this top position instead of the oxygen. You need to know that carbon monoxide is toxic because it replaces oxygen coordinately bonding to the iron 2+ in hemoglobin and substituting the oxygen out. This carboxyhemoglobin is a very stable complex, and carbon monoxide is much more strongly bonded. And so this ligand substitution is irreversible without medical treatment. And so it reduces the ability of the iron 2+ to carry oxygen around the body, and that's what makes the carbon monoxide toxic. Cisplatin is an anti-cancer drug, and it works by preventing DNA replication. This is a molecule of cisplatin here, and you can tell it's the cis stereoisomer because the 2 chloride ligands are next to each other. After cisplatin enters a cell, a chloride ligand is replaced by a water ligand, and this is an equation for it here. You can see that there are 2 chloride ligands in the first complex, and afterwards one of them gets substituted out and replaced with water. And then the water molecule is replaced by a new coordinate bond, forming between platinum and a nitrogen atom in a guanine nucleotide in DNA. And then the remaining chloride ligand is also replaced as another coordinate bond forms between platinum and a nitrogen atom in a second guanine nucleotide adjacent to the first. You can see here the platinum still coordinately bonded to those two original ammonia molecules, now bonded to the two guanine nucleotides. Here's the guanine base and the deoxyribose sugar and the phosphate group in one strand of DNA, and then in another strand of DNA we have a new guanine nucleotide with a further coordinate bond forming between a nitrogen atom and the platinum. These coordinate bonds stop the DNA strands from separating and replicating. You need to be aware that cisplatin is toxic, and it can cause side effects because it enters both healthy and cancerous cells. However, cancer cells absorb more cisplatin due to their higher blood supply, making them more affected. And so despite the risks, the benefits of treatment far outweigh them. One of the distinctive characteristics of transition metals is their formation of coloured ions, which means that transition metals can be identified by their colour. Colour arises when some of the wavelengths of visible light are absorbed. For example, if white light is incident on a sample, some of the light is absorbed due to the transition metal having an incomplete D subshell. We only observe the wavelengths of light that are transmitted or reflected. And so, if red, yellow and green light are absorbed, the remaining transmitted light will appear blue, as it is the complementary colour. This works with reflection from solid samples too. When white light is incident on a solid object, if violet and blue light are absorbed, the remaining light will be reflected, and the observer will see the object as being orange. And so solutions will transmit the light that is not absorbed, and solid samples will reflect the light that is not absorbed. And this absorption is due to the transition metal having an incomplete D subshell. And so something that does not have an incomplete D subshell cannot absorb visible light, and so will not appear to be coloured. Now that we know that substances absorb and transmit different colours, let's explore why this happens and why the colours are different for different metals. When ligands bond to transition metals, the 5 orbitals that are in the D subshell split into different energy levels. And you can see this from the diagram that I'm showing here. On the left-hand side, without ligands, we have 5d orbitals with the same amount of energy. And then with ligands, 2 or 3 of the orbitals have a higher energy than the others. Any electrons in the D subshell will exist in the lowest energy state, and this is called the ground state. D electrons will move from the ground state to an excited state when light is absorbed. And the light absorbed needs to give the electrons enough energy to move from the ground state to the excited state. Delta E is the symbol for this energy difference between the ground state and the excited state. Different wavelengths of light have different amounts of energy, and so delta E corresponds to the wavelengths of light that are absorbed by the metal compound. Since delta E is different for the different metals, this means that different wavelengths of light will be absorbed and transmitted, and so we will see different colours for the different metals. The energy difference between the ground state and the excited state determines the wavelength of light absorbed, and we can calculate it using Planck's equation delta E equals hV, where delta E is the energy difference measured in joules, H is the Planck constant, which has a value of 6.63 times 10 to the minus 34 joule seconds, and V equals the frequency of the light absorbed, measured in hertz or seconds to the minus 1. Frequency and wavelength are linked together in the wave equation, where wave speed equals frequency multiplied by wavelength. Wave speed is in meters per second, and wavelength should be in meters. Sometimes you will be given a wavelength in nanometers, and a nanometer is 1,000,000,000 times smaller than a meter. So to convert nanometers into a meter, you will have to divide this number by 1,000,000,000. This means that we can actually go back to the energy difference equation and have a substituted form for it where delta E equals Planck's constant multiplied by wave speed divided by wavelength. And this tells us that a smaller energy difference will mean longer wavelengths of light, so lower energy will be absorbed, while a larger energy difference will mean shorter wavelengths of light are absorbed, so in other words, higher energy. If an atom or ion has a completely full d subshell, there is no available space for the electrons to be excited, and so it can't absorb visible light and will appear colourless. Different transition metal compounds have different colours because the energy difference, delta E, varies between metals. But even complexes of the same transition metal can appear different colours, and this is due to a number of factors, such as changes in oxidation state, or coordination number, or changes to the ligand. All three of these will alter this energy difference, and since delta E equals hc over lambda, this will affect the wavelength of light absorbed, and this will lead to a change in the colour observed. For example, if we have the hexa-aqua iron 2 complex, this will be a green solution. But if the oxidation state of the iron changes from +2 to +3 for no change to the ligand, the colour will change to be a yellow solution. As a second example, if we have a copper 2+ complex with 4 ammonia ligands and 2 water ligands, it will appear to be a dark blue solution. But if all 6 of those ligands are substituted for 4 chloride ligands, this change to the coordination number and change to the ligand will lead to the complex now having a yellow-green colour. A very common exam question would be one that asks you why a particular complex has a particular colour. And the standard response that I recommend you use would be to start by saying that visible light is absorbed when d electrons are excited, and that only a particular colour of light is transmitted or reflected. And so you would only need to personalise this and vary it slightly from one complex to another depending on the colour. So for instance, why is the hexa-aqua iron 2 complex green? Well, you would say that visible light is absorbed and d electrons are excited, and only green light is transmitted or reflected, and the rest of the light is absorbed. You could also be asked why a particular metal compound appears to be a white solid or a colourless solution. And so you would need to say that this is because they have a full d sublevel, or they have no d electrons at all, and so that means that they cannot absorb visible light. And so that's why they appear to be white or colourless, because all of the light is transmitted or reflected. As well as being able to see different colours of complexes with the naked eye, the absorption of visible light is used in spectroscopy. An example of this is the use of a colorimeter, which is a machine that measures the absorbance or transmittance of different frequencies of light. A simple colorimeter can be used to determine the concentration of coloured ions in solution, as well as to identify complexes and study their electronic structure. A simple colorimeter will have a source of white light that emits light of all the different frequencies. And then we have a coloured filter, which absorbs the majority of light, and it selects the wavelengths of light that are most strongly absorbed by the sample. So in my case, I'm showing a red filter, and that will absorb all of the frequencies of light except red. And then we have a space for our sample, which will be in a container. And I'm choosing to have a blue sample, and that's why I've selected a red filter, because blue samples absorb the colour red very well. And so different concentrations of our blue sample will give a different absorbance of this red light. And after the light has passed through our sample, it hits a detector. And this detector will give us a graph of absorbance of this light versus the concentration of our sample. In order to know that the absorbance is only due to the sample and not some other factors, we need to make sure we set the absorbance to 0 with distilled water in a sample container before we measure the absorbance of our specific sample. It's important to make sure that these sample containers are always the same width, because the path length that the light travels through is directly proportional to the absorbance. In other words, a wider sample container would absorb more light. This process is much quicker to analyse samples than something such as titrations, and it also enables us to use a much smaller volume of our sample, and in fact we can reuse our sample after it has been analysed. You need to be able to describe how we can use colorimetry to determine an unknown concentration for a sample of something, for instance a solution containing copper-2 ions. And to do this, the first stage would involve the production of a calibration curve. To use a colorimeter to produce a calibration curve, we need to measure the absorbance for a range of known concentrations, and then plot a graph of absorbance versus concentration. The first thing that we would need to do is have our reference sample. This would be a sample container with just distilled water in it, and we would reset the colorimeter so that the absorbance for this sample was 0, and this makes sense because if our concentration for our sample is 0, the absorbance should be 0. And then we would substitute this sample container for one containing hexa-aqua copper 2+ with a known concentration, and we would measure that absorbance. And then we would substitute this out for a different concentration of copper 2+, measure that absorbance, and then another one, and then another one, and then another one, and we would keep repeating this until we have enough data to see the trend line for our graph of absorbance versus concentration, and we would connect those points with a line of best fit that needs to go through the origin, because if our concentration is 0, the absorbance should be 0. And then we would take our solution with an unknown concentration and put that into the colorimeter. We would measure the absorbance of this sample, and we would refer to our graph. We would find this absorbance on our graph, and we would read across to our best fit line, and then we would read down to the x-axis and read off the value for the concentration for this measured absorbance from the graph. An important property of transition metals is that they show variable oxidation states. For example, commonly iron can have an oxidation state of +2 or +3, and it can go higher. And manganese is commonly +2, +4 or +7, but it can also be +3, +5 and +6. Having the ability to change oxidation state is one of the features of transition metals that allows them to act as some types of catalyst. Under the right conditions, transition metals readily undergo redox reactions, where one substance is being reduced and the other is being oxidized. Remember, reduction is the gain of electrons and oxidation is the loss of electrons. For example, in the presence of certain reducing agents, transition metals can readily be reduced to lower oxidation states, and excess zinc is a very effective reducing agent. For instance, if we take a look at these two half equations here, where you can see we've got the oxidizing agents on the left-hand side ready to gain electrons, these half equations are equilibria, which means they are reversible. And on the right hand side we have the reducing agents. If we take a look at the electrode potentials for these two half equations, we can see that the larger electrode potential is for the iron 3+, our transition metal, which means this is the half equation that will go in the forwards direction, in the direction of being reduced. And the zinc half equation with the smaller electrode potential will go in the reverse direction, losing electrons. So the reducing agent, the zinc, is being oxidized. Overall, then, when we combine these two half equations, we need to double the iron half equation and then combine them together, remove the electrons, and we can see that this is the overall equation. And the E cell, or sometimes called the EMF, would be 1.53 volts. Transition metals show variable oxidation states, and in chemical reactions they can move between these oxidation states by gaining or losing electrons. Redox potentials indicate how easily an ion is reduced, and they follow the same principles as standard electrode potentials, namely 298 Kelvin temperature, 100 kilopascals pressure for gases, and 1 mole per decimeter cubed concentration for solutions. They are slightly different though, because where the standard electrode potentials are measured for metal aqua ions, the redox potential for a transition metal changing from a higher to lower oxidation state is influenced by the pH and the ligand. And some ligands form stronger coordinate bonds than water would in the metal aqua ion. Therefore, the redox potentials can be different to electrode potentials. In general, redox potentials are larger in acidic conditions, since hydrogen ions are often required for reduction. And you can see that this is the case here for this dichromate ion being reduced and turning into the chromium 3+ ion. You can see that there are hydrogen ions on the left-hand side of the equation, which means that their role is involved in this reduction of the dichromate ion. And so adding acid will decrease the pH and it will increase the hydrogen ion concentration. And so the equilibrium will shift to the right-hand side, and so there will be a larger redox potential in this situation for this low pH. In contrast, any added base would react with the hydrogen ions, thus decreasing the hydrogen ion concentration, and the equilibrium would shift to the left, and the redox potential would decrease. A common example of transition metals showing variable oxidation states is vanadium. In an experiment, you can reduce vanadium by reacting it with zinc in acidic solution. To do this, you would take a solution containing the vanadate 5 ion, for instance NH4VO3, and then you would add zinc to this solution. And the zinc metal would be oxidized, it would lose electrons and produce these electrons, which can then be gained by the vanadium. Initially, vanadium is an oxidation state of +5, which gives it its distinctive yellow colour. But then it can gain electrons in acidic solution and become a blue solution of VO2+, which has vanadium in a +4 oxidation state. But actually it doesn't end there. This vanadium in the +4 oxidation state can gain more electrons in acidic solution and become vanadium +3, which is a green coloured solution. And then finally that vanadium +3 can gain a further electron and become a vanadium with an oxidation state of +2, which is a violet coloured solution. You need to be able to combine the zinc half equation with any of these three vanadium half equations, or with more than one of these vanadium half equations at once. For instance, what is the half equation for vanadium +5 turning into vanadium +2? To do this, you start with the VO3 1- and we end with the V2+. To balance for oxygen atoms, we need to add 3 water molecules to the right-hand side, and then to balance for hydrogen, we add 6H+ to the left-hand side. And then to balance for charge, we need to add 3 electrons to the left-hand side. A number of these reduction half equations take place in acidic solution. You can tell that from the presence of the hydrogen ions. And the selection of acid is very important. For redox reactions, you will typically acidify with sulfuric acid. And this is because the sulfate ion is a stable ion and won't act as an oxidizing agent under these conditions, and so won't interfere with the redox process. Unlike with hydrochloric acid, where the chloride ion can act as a reducing agent and it can give electrons to potential oxidizing agents. And then nitric acid contains the nitrate ion, and the nitrate ion is a strong oxidizing agent and it can take electrons from other chemicals. And so sulfuric acid is definitely preferred. Like acid-base titrations, redox titrations are carried out to determine an unknown concentration of a solution. In exam questions, this is often part of a larger goal. You might be trying to find out the mass of iron in an iron tablet, or the percentage of iron in steel, or even the MR of hydrated ammonium iron 2 sulfate. You won't do all of these practical investigations during your lessons, so it's important to practice lots of exam questions to explore as many of these as possible. To carry out this titration, you would first transfer 25 cm cubed of an iron 2+ solution into a conical flask using a pipette. And then into the burette you would place the pink potassium manganate 7 solution. This chemical is oxidizing and harmful, and so whilst filling up this burette, you would make sure that you fill it up below eye level to prevent any solution splashing into your eyes or face. Potassium manganate 7 is a strong oxidizing agent, and during this titration it gains electrons and becomes manganese 2+ ions, and the colour changes from pale pink to colourless, and so this means that no indicator is needed for the titration. The iron 2+ solution is therefore oxidized and becomes iron 3+ by losing electrons. And in terms of the half equations, you can see that we've got the beginnings of half equations here. The manganate 7 equation needs to have 4 water molecules added to the right-hand side, and then 8 hydrogen ions added to the left-hand side. And then to balance for charge, we need to add 5 electrons to the left-hand side. The iron half equation just needs 1 electron adding to the right-hand side. It's important that you remember these half equations, or that you remember how to work these half equations out if you know the crucial chemicals on each side for the manganese and the iron. When you combine these two half equations, we need to multiply the iron half equation by 5, add the two equations together, and simplify out by removing the electrons. And this gives us the overall redox equation that I'm showing here, and you can see that the iron moles is 5 times larger than the manganate 7 moles, which is really important for our analysis. During the titration, the pink potassium manganate 7 of known concentration becomes decolorized when it is added to the conical flask. At the end point, it is no longer decolorized, and so the color change is from colorless in the conical flask to pale pink. After you've finished this titration and reached that endpoint, you'd note down the titer volume for potassium manganate 7 and work out an average volume needed to react with the iron 2+. And then you'd use the equation moles equals concentration times volume to work out the moles of potassium manganate 7 added to the conical flask, and then you'd use the mole ratio of 1 to 5 to work out the moles of iron 2+ that must be in that conical flask. And then, depending on the specific target of the investigation, you might follow this up by working out a mass value by using mass equals mR times moles. Redox titrations can also be carried out where potassium manganate 7 reacts with ethane dioate ions. And the overall redox equation is shown here, and it's important to note the 2 to 5 ratio that the manganate 7 and the ethane dioate ions react in. The half equations for this reaction have the ethane dioate ion turning into carbon dioxide and being oxidized. The ratio there is 1 ethane dioate to 2 carbon dioxide, and both of those carbon atoms lose 1 electron, so we need 2 electrons on the right hand side to balance this. The manganate 7 half equation is shown here. You can see the pink MnO4- is turning into Mn2+. We need 4 water molecules on the right hand side, 8 hydrogen ions on the left hand side, and 5 electrons being gained by the manganese, whilst this manganate 7 is acting as an oxidizing agent. You can see the hydrogen ions are reactants in this half equation and in the full redox equation, which is why this takes place in acidic solution. You can also see the electrons in the 2 respective half equations, and that's why the ratio is 2:5, because the common multiple for electrons is 10, and so the top half equation needs to be multiplied by 5, and the bottom half equation multiplied through by 2. An example of where this redox titration might be applied is to determine the MR of ethane dioic acid. To carry this experiment out, you'd dissolve a certain mass of ethane dioic acid in a beaker. This chemical is toxic, so you'd wear gloves whilst dissolving it. Perhaps you'd be given an exam question where they describe 200 milligrams as being dissolved in a beaker, and you have to remember to convert that mass into grams. And then you would dissolve it, and once fully dissolved, you'd make up a volumetric solution in a volumetric flask in some kind of volume, such as 250 cm cubed. And then you'd titrate 25 cm cubed portions of this solution in a conical flask with this manganate 7 ion from the burette, which is pink at the start. During the titration, the manganate 7 ions become decolorized, and so whilst it's pink in the burette, it would be colourless as it is added to the colourless ethane dioic acid solution, but then once all that ethane dioic acid has been used up, the colour change at the endpoint would be colourless to pale pink. You would note down the tighter volume added from the burette, and you'd use this value along with the concentration for the manganate ion solution to work out the moles of manganate 7 added from the burette. You would use that 2:5 ratio to note that there would be 2.5 times the number of moles of ethane dioate in the conical flask as you have added from the burette. And then you would also perhaps have to note that you'd only been reacting 25 cm cubed of your solution out of the total volumetric flask solution, and so you would need to factor that in by multiplying the moles of ethane dioate in the conical flask by 10 to work out the moles of ethane dioic acid in the volumetric flask, and hence in this 200 milligrams of ethane dioic acid that you'd started with. And then finally, since you know that the mass that you've used is 0.2 grams, and you know the moles by using the titration results, you can work out the MR of the ethane dioic acid by doing mass divided by moles. Sometimes redox titrations involve hydrogen peroxide. You'll usually be given the half equation for hydrogen peroxide and expected to use it along with the rest of the titration analysis. A potential goal for this titration would be to determine the concentration of hydrogen peroxide in hair bleach. The oxidation half equation for hydrogen peroxide has H2O2, with the oxidation state of oxygen being -1, turning it into O2 with the oxidation state of 0 for oxygen, plus 2 hydrogen ions, plus 2 electrons, showing that each oxygen atom is losing 1 electron to a total of 2. To do this titration, you'd first dissolve a sample of hair bleach in a volumetric flask and make the volume up to 250 cm cubed, and a 25 cm cubed portion of this would be removed with a pipette and placed into a conical flask and acidified, and then you'd be ready to titrate this with the potassium manganate 7. The half equation for the manganate 7 has got 5 electrons being gained in the presence of hydrogen ions, which is why we acidified the conical flask before starting the titration. And we produce Mn2+ and 4 H2O. Since 5 electrons are being gained by the manganate 7 and 2 lost by the hydrogen peroxide, we need to multiply those half equations by 2 for the manganate 7 and 5 for the hydrogen peroxide. When we combine those multiplied half equations, we get this overall redox equation that I'm showing here. And then one important thing to note is I've got hydrogen ions on both the reactant side and the product side. So it's really important that we simplify this by removing those 10 hydrogen ions from the product side, and we remove 10 of those 16 hydrogen ions from the reactant side to give us an overall redox equation that I'm showing here, showing that we need a 5 in front of the hydrogen peroxide and a 2 in front of the manganate 7, and those hydrogen ions are again showing that the solution needs to be acidified. Whilst we do the titration, the pink potassium manganate 7 is decolorized as we add it from the burette and swirl the reacting mixture, but at the end point the colour changes from colourless to pale pink because a tiny bit of that manganate 7 is left unreacted in the conical flask, and so that means that this is again self-indicating, so no indicator need be added. Then we'd work out the mean titer volume of manganate 7, multiply it by its known concentration using moles equals concentration multiplied by volume to work out the moles of manganate 7 added from the burette. Then we'd use the mole ratio from the redox equation of 2 to 5. We'd multiply that number by 2.5 to get the moles of hydrogen peroxide present in our conical flask, and then we would multiply that by 10 to work out the moles of hydrogen peroxide present in our volumetric flask in our diluted bleach solution. And we'd follow that up with some analysis that would vary slightly depending on the goal of the question. Transition metals and their compounds can act as catalysts. There are two different types of catalyst, heterogeneous catalysts and homogeneous catalysts. And before we take a look at both of these in more detail, let's remind ourselves about what catalysts are. A catalyst is something that speeds up the rate of a chemical reaction and is left unchanged by the reaction. In other words, it's not used up. And this allows for a faster reaction even at a relatively low temperature, and so therefore this saves energy and money and is more sustainable. Catalysts work by providing an alternative reaction pathway with a lower activation energy, and we can see the effect of this by looking at the Maxwell-Boltzmann curve I'm showing here. If this point on the x-axis is the activation energy without a catalyst, then the area under the curve after this point in the graph is proportional to the number of molecules with energy greater than or equal to the activation energy. If the activation energy is lowered by the use of a catalyst, then the area after this activation energy will increase since there is a bigger region of this area of the graph after this point. This means that more molecules will have energy greater than or equal to the activation energy, and therefore there will be more frequent successful collisions. Transition metals make effective catalysts because they have an incomplete D sublevel and because they have the ability to have variable oxidation states. A heterogeneous catalyst is in a different phase or physical state from the reactants. Typically, this will mean a solid catalyst and gas or aqueous reactants. One example of this from organic chemistry is the catalytic cracking of alkanes. For instance, tetradecane can be cracked into octane and hexene using a solid zeolite catalyst. For a second example, iron is used as a heterogeneous catalyst in the Haber process, where nitrogen from the air reacts with hydrogen from natural gas in a reversible reaction that reaches equilibrium and produces ammonia. The reaction occurs at active sites on the surface of the metal catalyst, and these active sites are often d orbitals of the metal atoms. A support medium is used to maximise the surface area of the catalyst and minimise cost. This makes sense since the reaction is only occurring at the surface of the metal, and so anything below the surface is not used and so shouldn't be expensive. We could also use powder or pellets or a mesh catalyst. For example, in catalytic converters, rhodium metal is coated onto a ceramic meshwork or honeycomb. The action of a heterogeneous catalyst takes place over 3 stages. The first stage is known as adsorption, and this is where the reactants bind to the active site on the surface of the catalyst. We might say that the reactants adsorb to the catalyst. And so if this was the Haber process, the hydrogen and the nitrogen reactants would adsorb onto the surface of the ion catalyst at the active sites, which I'm showing here in yellow. And then in the second stage, we have the reaction occurring. And this is where bonds in the reactants weaken, and then the reaction takes place. And this reaction will take place more quickly than the uncatalyzed reaction, since the bonds in the reactants have now been weakened, and that means that less activation energy is now required to finish breaking those bonds in the reactants, and so new bonds can form more quickly. And then the final stage is known as desorption. And this is where the products are released from the active site. So in this case, we would have our ammonia molecules being released from the active sites of the ion catalyst. We would say that they desorb from the surface of the catalyst. Heterogeneous catalysts can be poisoned by impurities that block the active sites, and this consequently reduces the efficiency of the catalyst, which has cost implications since the catalyst would need to be replaced. One example of this is in the Haber process, where the ion catalyst can be poisoned by sulfur. And you can see that I'm showing that in the ion catalyst here with the 4 yellow active sites. And then the more sulfur that is present in the reactor, the more of these active sites will be blocked, and the greater the reduction in the efficiency of the catalyst. A second example of this is in catalytic converters, where the platinum catalyst can be poisoned by lead, and again, those lead impurities bind to the active sites irreversibly and block them. Some catalysts are more efficient than others. Sometimes the catalyst might adsorb too strongly to the reactants, and this would prevent the reactants from desorbing. So that means the catalyst will bind to the reactants and not let go. And sometimes we can have the opposite problem, where some catalysts adsorb too weakly to the reactants, and so the bonds in the reactants don't weaken sufficiently to speed up this reaction. Generally, transition metals in the middle of the D block make better catalysts than those at the ends. On the left-hand side of the D block, we find the elements that typically adsorb too strongly, and on the right-hand side of the D block, we find those elements where the adsorption is too weak. You need to know about a number of specific catalyzed reactions from across the chemistry course, and one of them is from the contact process, where vanadium 5 oxide, V2O5, acts as a heterogeneous catalyst to support the production of sulfuric acid. The overall reaction is 2 sulfur dioxide molecules react with 1 molecule of oxygen to produce 2 molecules of sulfur trioxide. And then this sulfur trioxide reacts with water to produce the sulfuric acid. You need to be able to explain, with the aid of equations, how this process works. Typically, for the examples that you need to remember, the catalyst reacts with one of the 2 reactants and produces an intermediate, and then this intermediate reacts with the second reactant. And that's what takes place here. First of all, the V2O5 reacts with the sulfur dioxide and produces V2O4 and sulfur trioxide. We can say that the vanadium has been reduced because it's lost oxygen, and its oxidation state has gone from +5 to +4. This V2O4 then reacts with the oxygen and reforms that V2O5, and the oxidation state returns from +4 back to the +5. And we can see that the V2O5 is acting as a catalyst because it is used up in the first equation and then regenerated or reformed in the second, and the V2O4 is an intermediate which is made in step 1 and reused in step 2. If we then add those equations together, remove the intermediate and the catalyst because they are unchanged, we get the same equation as before. Sulfur dioxide reacts with oxygen to produce sulfur trioxide. This shows that the vanadium 5 oxide provides an alternative pathway for the reaction, and it can catalyze this process as it has variable oxidation states. A homogeneous catalyst is in the same phase or physical state as the reactants, and this is likely to be where everything is in aqueous solution. For instance, where concentrated sulfuric acid is used as a catalyst to produce esters from carboxylic acids and alcohols. One example from earlier in the course where the reactants and the catalyst are all gases is where chlorine free radicals catalyse the breakdown of ozone gas into oxygen gas. When catalysts and reactants are in the same phase, the reaction proceeds through an intermediate species, and this typically works because transition metals have variable oxidation states. And so as it works, the catalyst will donate electrons to something or accept electrons from something and form an intermediate species. And this intermediate will then accept electrons from something else or donate electrons to something else and remake or regenerate that catalyst. Since this reaction is proceeding through an intermediate species, the reaction profile for a homogeneous catalyst looks different to the typical reaction profile. You can see here I'm showing the purple pathway for a typical reaction where the reactants are converted into the product, and this is the activation energy that I'm showing here, and this is the energy change. When we've got a homogeneous catalyst producing an intermediate, we have a third horizontal line representing the energy of the intermediate species. And that means we have two separate activation energies. We have the first peak in the profile, and so this is the activation energy number 1. And then we have the second peak in the profile, and so this is activation energy number 2. Notice, of course, that the energy change is the same for both of these pathways because the energy of the reactants and the products is the same for both the purple pathway or the blue catalyzed pathway. A very common example of homogeneous catalysis that you need to know about is when iron 2+ catalyzes the reaction between iodide ions and peroxodisulfate ions S2O8 2-. The overall reaction is the peroxodisulfate ion reacting with 2 iodide ions and producing 2 sulfate ions and iodine. If we take a look at the oxidation states, we can see that in the peroxodisulfate, each of those sulfur atoms has an oxidation state of +7, whereas in the sulfate ion, each sulfur has an oxidation state of +6. What that means is that each of these sulfur atoms is gaining 1 electron, and so they are both being reduced. And then looking at the iodide ion, the oxidation state is -1, and then in iodine it is 0 because all elements have an oxidation state of 0, and therefore each of those iodide ions is losing 1 electron. In other words, they are being oxidized. And so this seems like a simple redox reaction where those iodide ions are giving their electrons to the sulfur atoms. So then why does this reaction need a catalyst? Well, the answer is because the activation energy is very, very high. And the reason for this is that both of these ions are negatively charged, and so they repel each other. And then the role of iron 2+ as a catalyst then is as an electron transferer. And what I mean by that is the iron 2+ can be an electron donor and turn into the iron 3+ and releasing that 1 electron. And then the iron 3+ can act as an electron acceptor and take an electron from a second chemical and turn back into the iron 2+. And so in more detail, we can see that the iron 2+, the electron donor, is going to react with the sulfur in the peroxodisulfate because that needs to gain an electron. And that then converts this into 2 of the sulfate ions and 2 of the iron 3+. We need that balancing because each iron 2+ is only losing 1 electron. And then this iron 3+ is an intermediate, which means it's made and then it's reused. And so that iron 3+ then takes an electron from an iodide ion to produce iodine and iron 2+. Note again the balancing is we need 2 of those iron 3+ because there's 2 iodide losing 2 electrons. And this therefore proves that the iron 2+ as acting as a catalyst because we had it at the start of the first equation and it's regenerated at the end of the second equation. And this is all made possible because of the variable oxidation states of the iron. The 2+ loses electrons to become a 3+, and the 3+ then accepts an electron to turn back into the 2+. We can use redox potentials as a justification of the selection of iron 2+ as a suitable catalyst, because not only does the transition metal need to have variable oxidation states, it also needs to have an electrode potential value that is between the values for the 2 reactions being catalyzed. If we take a look at those 2 half equations for the reduction of the peroxodisulfate and the reduction of the iodine, first of all, remember we've got our electron acceptors on the left-hand side, those oxidizing agents, and we've got the reducing agents on the right-hand side that are electron donors. Taking a look at the electrode potential for the peroxodisulfate half equation, that value is 2.01, whereas the iodine half equation is 0.54. And this proves that the peroxodisulfate can take electrons away from iodide ions, and the E cell for this reaction would be 1.47 volts. But again, the repulsion between the iodide and the peroxodisulfate gives us this high activation energy. The electrode potential for iron 3+ gaining an electron and turning into iron 2+ is 0.77 volts, and this is really crucial that it's between those other two, because the peroxodisulfate electrode potential is greater than the iron 3+ electrode potential, and therefore iron 2+ is able to reduce peroxodisulfate, and in fact the E cell would be 1.24 volts. But the electrode potential of iron 3+ to 2+ is greater than the electrode potential for iodine turning into iodide, and so that means that the iron 3+ is able to oxidize the iodide ions by accepting electrons from them, with an E cell or EMF for this reaction being 0.23 volts. Autocatalysis is where a product of the reaction catalyzes the reaction itself. The main example that you need to know about is when manganate 7 ions react with ethane dioate ions in acidic conditions to produce manganese 2+ ions, carbon dioxide, and water. This is a redox reaction because the manganese in the reactants has an oxidation state of +7 and in the products it is +2, showing that it has been reduced by accepting 5 electrons. And the carbon in the reactants is +3 and in the products it's +4, suggesting that each of those carbon atoms has donated 1 electron to the manganese. This reaction is very slow at first because the manganate ion and the ethane dioate ion are both negatively charged, and so they repel each other, and this means that the activation energy is very high. But as the manganese 2+ ion is produced, the reaction rate will speed up because manganese 2+ ions can catalyze this reaction. And this is made possible because manganese 2+ can be oxidized into manganese 3+, producing 1 electron, and then it can be reduced back into manganese 2+. And so in the first part of this reaction, manganese 2+ is oxidized by the manganate 7, and it gives the manganate ions electrons and forms Mn3+, which is then reduced back to Mn2+ by the ethane dioate ion, and the ethane dioate ion gives electrons to the manganese 3+. You need to be able to write equations that show how this catalysis occurs, and I think the best way to do that is to sequentially combine the manganese 2+ equation with the 2 half equations for manganate 7 and ethane dioate. You can see for the manganate equation that 5 electrons are being gained and the manganese 2+ only loses 1 electron. So we need to multiply the manganese 2+ equation through by 5 and combine those 2 equations together. And so we're left with this. But what you should notice about this equation is that there are 5 manganese 2 plus ions on the left-hand side and 1 on the right-hand side. And we need to remove the 1 from the right-hand side and 1 of the manganese 2 plus ions from the left-hand side, and that gives us this equation taking place for the first step. And then the manganese 3 plus, when this equation goes backwards, 1 electron is gained, but the ethane dioate ion loses 2. So we need to again multiply the manganese equation. This time it's by 2, and we get this overall equation for this second step of the reaction. This proves that the manganese 3 plus is an intermediate chemical because it's made and then reused in the second step, and the manganese 2 plus is a catalyst because it's used in the first step and then regenerated in the second step. And then we can combine these 2 steps of this alternative reaction pathway by multiplying the top equation through by 2 and the bottom equation through by 5. And then that allows us to combine these 2 equations to this one very big overall equation. But what you can see is that because of how I've multiplied those 2 equations, we now have 10 manganese 3 plus on both sides of the equation. So that means that we can successfully remove our intermediate chemical. And then we have 8 manganese 2 plus in the reactants and 10 manganese 2 plus in the products. And so we can remove 8 from both sides. And so that just leaves us with 2 in the products. And then this equation has been simplified down to the one that we began with at the top of the page. We can investigate the action of manganese 2 plus as an autocatalyst by carrying out a reaction between ethane dioic acid and potassium manganate 7. And you can see we've got a reaction mixture here with potassium manganate 7 and ethane dioic acid. This mixture would start off pink due to the manganate 7 ions, and the goal of our experiment would be to find out how the manganate ions concentration changes over time. To do this, we would need to remove small samples of our reaction mixture at regular time intervals. And each time we remove this sample, we would need to quench the reaction. That means we would need to stop the reaction. And this is because if we didn't stop the reaction, it would just continue, albeit on a smaller scale, in the little sample that we'd removed. And so we need to stop the reaction so we can analyze the concentration of the manganate 7 that was remaining at the point of removal. And so to quench this reaction, we could do one of a few things. For instance, we might dilute the reaction mixture significantly, or we might cool it in ice. Both of these things would drop the rate of the reaction down to effectively 0. And then we would need to analyze our reaction mixture to determine that manganate 7 ion concentration. We have 2 options here. First of all, the manganate 7 has a pink colour, and this will get paler and paler as the reaction progresses. And so it could be investigated using a colorimeter, and this would be very effective since the absorbance measured by the colorimeter would be directly proportional to the concentration of manganate 7 ions remaining. Or you could measure the actual concentration of manganate 7 ions using a redox titration. You could then analyze the results by plotting a graph of manganate 7 ion concentration against time. And if a catalyst had been added from the start, we would expect the shape of the graph to look like this, where we'd have a very steep gradient at the beginning, which is showing that the rate of reaction would be very fast, and then the reaction would slow down and the gradient would get more gentle, and then the reaction would finish. If the reaction was uncatalyzed, we would expect the shape to be slightly different. At the beginning, in this region of the graph, we would have a very slow reaction because there was no catalyst present at the beginning, and so the gradient would be very gentle. But then the reaction will speed up once the manganese 2 plus catalyst has been produced by the reaction. And so the gradient of that slope will increase. And this is proving that the reaction is making its own catalyst. In other words, the manganese 2 plus product is acting as an autocatalyst. And then, as with the catalyzed reaction, this reaction would slow down as the manganate 7 ion concentration decreases, and eventually the reaction would come to a finish.